So this one is number 2 of the 2018 free response, so you can still use calculator on this one. Alright, we're just going to start with A. So they want us, oh, well, we have to read it first. You're investigating plankton, and this function tells you the density of plankton in millions of cells per cubic meter for 0 to 30. And anything greater than 30 is modeled by f of h, which we do not know. Alright. So they want us to find p prime. Let's just get rid of this. P prime. So this derivative of this at 25. So literally just p of h. So what you're going to put in your calculator, all you have to write really is this equals whatever it equals. So what you're putting in your calculator, like let's say you're using Desmos, you're going to write d fraction dx, because that tells the calculator you're doing a derivative. And then you're going to write in your function. So that's this 0.2 h squared. Oh, but you're going to use x's, because I put an x here. So whatever variable here has to match the one on the inside. And calculators generally understand x's better, so just make it an x. Oh, I forgot my... There you go. So you're going to put that, and then you're going to put x equals 25, because that's... If we replace h with x, then that means instead of h equaling 25, it's going to be x equaling 25. And then you just look at where they intersect. So they intersect at negative 1.179. So that's our answer. So the only part you have to write is this. That's the only thing you have to write. That's you like showing your work, because they understand you have a calculator. Okay, and then it says interpret the meaning in the context of the problem. So whenever they say in the context of the problem, that means they want you to use units. So let's think about this. If this function is telling us millions of cells per cubic meter, and we integrate that, I mean we take the derivative of that, that means like that. So d of p over dh. So p of h is given by just making marks, millions of cells per cubic meter, and dh is just meters, because remember it says here at depth of h meters, so h is just meters. So the unit for this value is millions of, or what does it say? Millions of cell per cubic meter. Millions of cells per cubic meter. And then this derivative, this dividing sign and this meters together means per meter. So you see how this is like per cubic meter? This is per meter. So millions of cells per cubic meter per meter. Now I know Mr. Palmer combined these and would probably just write per meter, I don't know, to the fourth, but that's kind of weird. Like it's not wrong if you write this, but a lot of times the College Board just leaves it as per something. So it's fine if you write per cubic meter per meter. And it sounds better anyways if you want to, since we're writing it out in words. So now that we know what the unit of that is, per million cells millions of cells per cubic meter per meter. And this is our H. So what is H telling us? It tells us the depth that we're investigating plankton at. So essentially, and remember, derivative is, this is the number of plankton. So the derivative of that would be the rate of change of plankton, because it's like going from, remember, position to velocity. You take the derivative. So, oops. So, at a depth of 25 meters, the density of plankton. Okay, so now there's two ways to do this. You can either say it's changing at a rate of negative 1.179, or you can say it's decreasing at a rate of 1.179, because saying the decreasing is saying that negative part. So I'm going to say decreasing because I think it sounds better, but if it's easier, just write changing at a rate of that. Because honestly, that is easier, since P prime is a rate of change, and you don't have to worry about whether it's like, think about whether it's decreasing or whatever. But I'm going to write the density of plankton is decreasing at a rate of 1.179, and then our unit that we just figured out. So millions of, no, it's just million cells. Millions of cells. Okay, I can write millions of cells. Or million cells. It's the same thing. Million cells per cubic meter per meter. So that's our answer. And then, so this one's worth 2 points. It's just one for that, your answer. This is your answer. And then one for interpreting it with units. So that's that there. Okay, now part B. A vertical column of water with a horizontal cross-section of 3 square meters. And how many plankton are in that? So, okay, so to understand this, I'm going to draw a little picture for you. Here's our boat that we're using to investigate plankton on. And this is like the sea. Okay, and then we have a cross-section with a constant area of 3 square meters. So, boom, boom, boom. So that's the area that we're investigating. So it starts, this is us on top of the sea, and this is how deep we're going to investigate plankton. So this is H, and it's split into horizontal cross sections of constant 3 square meters. So like a slice of this, that's what it means. A slice of this has an area of 3 meters squared. What a nice little drawing. And then how much plankton are in there? So we're essentially adding up cross sections all along this H depth. So that means we're going to take the integral of this H. And remember, the number of plankton over this depth is measured by this P of H. So that means we want to take the integral from 0 to 30, because it tells us that they want us to go from 0 to 30. Forgot to mention that part. Of P sub H dH. Okay, so now if we think about the units of this, P of H is measured in millions of cells per meter cubed. D of H is just meters. So this is times meters. just write over 1. So when you take the integral, those multiply, cancel it out. So the integral unit, the unit of the integral would be millions of cells per meter squared. And this unit is in meters squared. So to find out how much plankton is in one of these sized slices, we have to multiply it by 3. And we can do that because the units match after taking the integral. Okay, so now you just put that into your calculator. Well, of course, instead of writing P of H, you write that. And I'm just going to tell you right now, the answer is 1,675.4149, but I'm just going to round it to 415. And then we want to write our sentence, so never forget to write your sentence of the answer. So it's asking us how many plankton are in this column between h equaling 0 and h equaling 30. I'm going to write there are 1,000. Oh, it says to the nearest million as well, so this is going to round down to 1,675. So 1,675 million plankton cells in the column of water between h equaling 0 and h equaling 30. So that's how I would format the response. So always remember, just plagiarize them. It's easiest that way. So this one is also 2 points. Get 1 for this integral, and then 1 for writing your answer out. Okay, next one. So part C can be kind of confusing, and it's a lot to go over. So let's break this down. You have a different function that is bigger than f of h. And remember, our f of h is describing how much plankton there is for depths greater than 30 meters. So this one is only for depths up to 30 meters, and our f of h is for depths greater than 30 meters. So we have another function called u that is bigger, even bigger than our f of h. And they're telling us that the integral from 30 to infinity is equal to 105. And our column of water in B is k meters deep, and k is greater than 30, so they're just giving it a name. And we want to write an expression that can explain the number of plankton in the entire column, and then show that it's less than or equal to 2,000 million. 2,000 million. Interesting number. But yes. Okay. So first, we have to interpret what this means for our previous expression in terms of k. So we're going to k meters. So from 0 to, from 30 to k, because k is greater than 30, and p of h models anything less than 30. From 30 to k of f of h, because remember, f of h is for any depth greater than 30 meters. And we have to multiply by 3 because the column of water is from part B. And in part B it says it was 3 square meters. Okay, so that's why we multiply that by 3. So what does this represent? This represents, or I'm going to say, is the number of plankton cells from a depth of 30 to k meters. Because k is just some number greater than 30. We don't know what it is. So in the entire column, we have to add this plus our number of plankton for the depth from 0 to 30. So going from 0 to 30 and then 30 to k is our number of plankton in the entire column. So 0 to 30 of p of h dh times 3, remember, because that's the size of our column, plus 30 to k f of h is the number of plankton cells per million, or I'm just going to say in millions, is the number of plankton cells for the entire column. Okay. And then we're going to bring in this part, because we don't know how well, actually it's telling us that the column is k meters deep, and k is just some number greater than 30. Okay, so now to figure out, so this is our integral for the number of plankton in the entire column. Okay, and then we have to show why it's less than or equal to 2,000 million. So that's where we bring this u function into the equation. So we know that, what does this say? 0 is greater or less than or equal to f of h, which is less than or equal to u of h. So that means this integral that we use to explain like the second half of our entire column from 30 to k of f of h dh, this is less than if we used a function like u of h to explain the entire column dh. Because remember, u is greater than f. So that means if we used u to explain the number of plankton from 30 to k, from a depth of 30 to k, this integral would be bigger than this integral. And going even one step further, an integral going from 30 to infinity with u sub h dh would be even bigger than this one, because instead of stopping at a number k, this integral depth, this hypothetical depth, goes on for forever. And we have a function that explains an integral from 30 to infinity, which is equal to 105. So if we replaced this part with 105, we get 3 times 105. So that's equal to 3 times 105, which is 315. So this is like the maximum number of plankton cells that we could have after a depth of 30 meters. So we're going to add that to the number of plankton cells that we have from 0 to 30, because then that would give us the number of plankton cells at a maximum, because it's going to infinity, number of plankton cells for the entire column. So this number was, what was it? 1,675.415. Okay, 1675.415. And then we're going to bring this one into it, plus 315. And that equals 1989. What? Wait, this is a 5. I'm not doing my math right. 90.415. Goodness. And 1990.415 is less than 2,000 million. So this in a sentence is, I would say, the total number of plankton cells in the column of water is bounded by 1990.415. And the reason we say bounded is because this goes on to infinity. So that is like the maximum amount of plankton cells that you could have in that column of water, because the depth goes to infinity. So there's nothing bigger than infinity. And we only stop at K. So we know for sure that there's even less plankton cells in the column than this. And if this is less than 2,000 million, then for sure the number of plankton cells, the actual number, is less than 2,000. So that is our reasoning for why the number of plankton cells in the column is less than or equal to 2,000 million. Because this is bounded by this number. So at the very, very maximum, if the depth went on for infinity, it would not go past that number. Okay, so this one was 3 points, which is kind of sad. Doing all that for 3 points, but yeah, this one was a hard question. So you get 1 point for this. Let me erase this. You get 1 point for this integral expression about the number of cells in the entire column. You get 1 point for this comparison of all three integrals, and then you get 1 point for that explanation. Okay, the last part is D. So a boat is moving on the sea. At time t is greater than or equal to 0, the boat is at this position. And this is the derivative of each of those. So we're trying to find the total distance traveled over the time interval 1 to 0. Okay. So, I forgot to mention, this is a parametric. Oh, I forgot to talk about that. I just got straight into the problem. Well, I'll do that after, but sorry. I got too excited. So, this is a parametric question, because we're talking about things in regards to this part is parametric because we're talking about things in regards to time. So whenever you see this format of not just x and y's, but x of t and y of t, let's talk about these functions in regards to time. And that's essentially what a parametric function is. It's a function in with regard to time. So when you're talking about total distance with a parametric function, it's the same formula as arc length. So remember, arc length is from a to b of the derivative of x squared plus the derivative of y squared. And everything is in regards to time. So they want us to solve this from 0 to 1. So that means our interval is from 0 to 1. And then I'm just going to write x prime of t. Let me put a bracket. Because you don't have to bother writing out the entire actual function. Just put that in your calculator. They just need to know that you know that it's that function. So this is this function. And this one goes right here. Okay, so when you put that into your calculator, the number that you get, wait, I forgot my dt. Don't forget your dt. The calculator is not going to know what you do if you don't have dt. So the number you get out of that is 757.4558. But I'm just going to round it to 456. And then remember, write your sentence. So they were asking total distance traveled by the boat over time interval 0 to 1. So I'm going to write 757.456 meters because they're measured in meters. And this is the total distance traveled by the boat. And what was the rest? Over the time interval 0 to 1. Over the time interval 0 less than t less than 1. So this one's also 2 points. Oh, I forgot to write this. The 3, 2. So 2, 4, 2, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yeah, so it's a total of 9 points. I don't know what I said 7 for. So 2 points. You get 1 for this integral with arc length, and then 1 for your answer. So that is number 2 about parametric. Oh, as for what a parametric function is. So if I had a line on a graph that looked like this. Okay. And it looked like this. This is not a function. Because a function means you only have one y output for each x. But like if I had an x here, I have a y output here, here, and here. That's what you call the vertical line test. So this one's not a function. But if we make it so that this change in x and y values is in regards to time, so over time you go from here to here to here to here to here to here, you're just moving along it like this. I guess I shouldn't put this arrow on the other side then. Yeah. So over time you're going like this. Then it becomes a viable function. So instead of us writing the points in terms of x and y, we write it in terms of x and y in terms of t. So y sub t and x sub t, because these become related to time. So over time, it follows this route. So that's what a parametric equation is. That's how you get around this vertical line test thing. Okay, so that is parametric FRQ.